Welcome back. We have taken our black hole journey from understanding space-time and Einstein to event horizons to Schwarzschild radii, and it's now time to think about what happens at the surface of a black hole. What is the surface of a black hole? Again, there's no real actual surface of a black hole, at least outside of what we think is a singularity at the center. The surface is usually what we talk about as that radius at which the escape velocity is equal to the speed of light, because this is the point of no return for a black hole. I already mentioned all of this stuff, but here it is in a slide so you can write it down, known as the event horizon and the Schwarzschild radius. There may be something physical below that where there is a physical surface to something, but we don't know what that is. And it doesn't really matter because we could never observe it. The event horizon really, for us, defines the boundary of the black hole, because anything that crosses that surface is lost to the rest of the universe. It can never come back, and it can never communicate with anything outside of the black hole. So that's why we have surface here in quotation marks. And it's not even all that much bigger than a neutron star. Here we have a 3 solar mass black hole. Remember our formula from the previous video. A 3 solar mass black hole has a radius of 9 kilometers. Just multiply this by 3, which is not that much smaller than the 10 kilometers of the neutron star. And so a neutron star is already pretty close to its event horizon. You don't have to squeeze it very much to actually get it to be the size of a black hole or so. Okay, so here's a survey question for you. I want to know, what do you think would happen if the Earth, and in particular the Earth's orbit, if the sun were suddenly replaced by a 1 solar mass black hole? Do you think that it would be sucked into the black hole? Do you think it would become unbound and fly off into space? Do you think it would remain in orbit around the black hole but with a much shorter period? Or would it remain in orbit around the black hole with exactly the same 1-year period? Go ahead and make your guess, and then come back and we will talk about it. Okay, welcome back. How many of you said A, it would be sucked into the black hole? Raise your hand. You're not alone. This is a very common misconception about black holes. In fact, if you remember nothing else about black holes, make it this. Black holes don't suck. They are not giant cosmic vacuum cleaners simply sucking up everything around them. They are no different really than any other mass. So let's try to figure out how that works in the next slide. And I think this video or this animation will make this hopefully clearer. So let's think about, here we go. Okay, so here we have an object, and this is, say, the sun. It's got a fairly large radius as radii go of things that we're talking about, and it's got a reasonable mass. And we're looking at this in the same way we looked at it before, thinking about space-time as a curved object. And we're thinking about a 2-dimensional view of the space-time around this massive object, because it's impossible to visualize this stuff in 3 dimensions. So this is equivalent to the toy at the Science Center that we talked about in the previous video. Put the quarter in, it orbits around and eventually falls in. The Earth is exactly like one of those coins, except there's no friction, and so it doesn't spiral in, and so it just remains in orbit around this thing. Okay, so what's going to happen if I make this object less massive? I'm going to move this slider bar to the left. What do you think is going to happen to the curvature out here if I make this object less massive? What's your prediction? Say it out loud, write it down. All right, let's actually move the slider bar and see what happens. Oh, it becomes less curved, which isn't terribly surprising, right? The more massive you make an object, the more it curves space-time in the region around it, and therefore the higher force of gravity is felt by things that are right around these things. To make this thing too massive, it becomes a black hole, and it's lost. You have an event horizon then that grows from there. But let's just think about our star again, and thinking about, so decreasing the mass decreases the curvature in a particular radius, and increasing the mass increases the curvature at a particular radius. What's going to happen if I move the object radius bar? Let's say I'm going to make this object bigger or smaller without changing the mass. How do you think that's going to affect the curvature out here? Let's do it. Making the object bigger, making the object smaller. How is that affecting the curvature in the space-time out there? It's not, right? An object that's orbiting out here has no idea, really. It doesn't care how big this thing is that it's orbiting. It doesn't change the curvature of the space-time at this distance from the center of that object. All that you do by making this thing smaller, is you make more space available. You can get closer to the center of it. And so space-time is curved in this region right around it more than it was before. But this space didn't even exist. It was inside the physical object before. It just allows you to get closer to the center of that object and experience higher space-time, higher curvature of space-time, until it's curved too much and it just goes to be a black hole, right? But for the purposes of our question, which was what happens to our planet out here, if it were replaced with an object that had exactly the same mass as the sun, the curvature out here is not affected at all by what the radius of this object is at the center. The Earth would be unaffected. It would still orbit in a perfectly happy 1 year period, going around the black hole as normal. It would not be sucked in. Black holes don't suck. They're just massive objects in space. Right, now other bad things would happen to the Earth, right? It's sitting here, if the sun goes away and is replaced by a black hole, obviously life dies out fairly quickly because there's no energy reaching us anymore and bad things happen. But the orbit is actually unaffected. Okay, let's go back. Great, so we've already talked about this as well, but here it is in words. Nothing can escape from within the event horizon, because within the event horizon, the escape velocity is faster than light, and nothing can go faster than light. And I mentioned this also, there is no contact with anything that does fall in. In fact, there is only these 1, 2, 3 things that you can know about a black hole. You can know its mass, you can know how fast it's spinning, and you can know what charge it has. Every single other property of a black hole, what it's composed of, what color it is, how large it is physically inside of there, not only isn't known, but cannot be known. There is no measurement that you can make from outside of the black hole that will tell you any of that information. All you can know is the mass, the spin rate, or the charge. Anything else loses its identity entirely when you fall in. I've already mentioned this term as well, the singularity. Again, we know of no known force that can hold this star up against neutron star collapsing and above gravity. For all we know, it collapses down into a single point, a singularity, with 0 radius. That's what we mean by a singularity. But even if it doesn't, even if there is some unknown force that holds it up from being a perfect singularity, nature doesn't really like singularity. So it's possible if that's the case. It doesn't really matter. We'll never be able to observe it. So from the outside, an object that has some physical radius or an object that has no radius look exactly the same. They're all still a black hole with an event horizon exactly the same place. Okay, other things, strange and odd things and uncomfortable things do happen at the surfaces of black hole. Let's talk about those real quickly. One of them is gravitational redshift. This is a little bit hard to understand. Let me try to explain this. Normally, if I were standing in the front of the class, I would, at this point, pick an eraser up from the whiteboard and throw it up into the air. And what's going to happen to that eraser? Well, obviously, it's going to move up. It's going to slow down, though. It's going to reach some maximum height, and then it's going to fall back down, and hopefully I will catch it. Right? The kinetic energy of an object, as I throw it up, decreases as it moves away from the gravity source, away from the Earth, until it stops. And then that energy is converted back into kinetic energy as it moves back down. But it has to lose some energy as it moves away from this gravity. It has to gain potential energy and lose kinetic energy. Well, light has to behave in exactly the same way as matter does. It can't just move away from this massive object and not lose energy. Light photons, though, cannot lose speed. They don't lose kinetic energy. They can't lose energy by changing their velocity the way an eraser can when I throw it up into the air. How can a light wave lose energy? There's only one way. If you remember the formula that we wrote down for the energy of a photon at the beginning of the semester, and we're talking about light, let's actually do this. Here's our whiteboard. Remember our energy of a photon, there's two constants, Planck's constant and the speed of light, divided by the wavelength of that photon, right? H and C are constants. Lambda is the wavelength, the waves of the photon. The only way for a photon to lose energy is to change its wavelength. And that's exactly what happens to photons as they leave near the surface of a black hole. If the energy goes down, that implies that the wavelength must go up, which is why, we go back to our slide, we refer to this as a gravitational redshift. Remember, redshifts, Doppler redshifts was objects that are moving away from us and therefore move toward longer wavelength. Gravitational redshift has to happen in the same way. Objects that are close to the event horizon, light particles that are emitted from close to, obviously a light particle emitted inside the event horizon isn't going to get out. But a particle that's emitted, a photon that's emitted near the event horizon will be much redder than it should be because it's lost energy escaping that potential well of the black hole itself. It will move towards longer wavelength. It will appear redder than it should. So that's odd. So let's do this one too. Let me see if I can open this up. Time near black hole. Bear with me for just a second. Uh-oh, where'd it go? That didn't work. Chapter 23, time near black hole. Doesn't seem to be there. Okay, well, oh, here it is. I think I found it. Okay, let me share this with you. Apologies for that delay. Okay, hopefully you're seeing this now. As somebody calls me on my cell phone. Great, it's all falling apart at the end of black hole day. All right, here we go. Gravitational time dilation redshift. So this is interesting, right? You've got two rockets that are orbiting the black hole. Let's just play this and let time run forward and see what happens. One of these objects, I think it's going to be this one when it gets to the bottom, is going to turn on its jets and fall into the black hole. Let me stop it here. If nobody turns on their jets, these guys are just happy orbiting this black hole. Nothing unusual happens other than somebody who's way out here will see their clocks running a little bit slower. This rocket wants to fall into the black hole. What's it going to have to do when it gets down here? It's going to have to fire its rocket. In which direction is it going to fire its rockets to get to the black hole? You might think it would fire it down to get to the black hole, but that's not the actual best way to do it. It's going to fire it in this direction. All it has to do is slow itself down. If it can stop its orbital velocity, it will fall directly into the black hole. And so that means firing in a direction opposite of the direction it's moving is the most efficient way to get into the black hole, interestingly. All right, this isn't exactly how it's going to work, but it's going to start falling into the black hole now, and you're going to see two things happen. One is these clocks are no longer going to be synchronized and agree with one another. As this guy gets closer and closer to the event horizon, time is going to run slower and slower. And the other thing that's going to happen is it's going to get redder and redder. Time is running slower and slower. It's getting redder and redder. Time is running slower and slower. It's getting redder and redder. Time is running slower and slower. Slower and slower. Slower and slower. Slower. And that's pretty much it. This rocket ship will get slower and slower and slower and slower And this rocket ship that's still outside will never actually see the probe that it sent into the black hole cross the event horizon. Time gets slow, so slow at the event horizon surface that it's basically not running at all. So what will happen, you'll just see this thing get slower and slower and slower and redder and kind of fade away into nothingness. So that's exciting. Let's go back to our PowerPoint slide. We're almost done with lecture for today. It's a lot, but it's Black Hole Day. So exciting. There we go. Okay. So what happens if you were to fall into a black hole? Now, bad things are going to happen because let's actually. Oh, well, I'll make one more video today. I'm already at 15 minutes on this one. So let's make one more video. I don't think it'll be long, but I'm going to make one more video and we'll talk about what actually happens as you fall into a black hole.